Okay, Assalamualaikum and good evening, students. So since today we don't have class, since many of you are joining with the career fair and so on, so please watch this video for today's lecture, which will be on structural interpretation of seismic reflection data. By the way, since I'm taking this class after Dr. Maman, so this will be my lecture plan and lab plan. We have done our fault picking and characterization activities yesterday during the lab. Only some of you turn out to the class. So we have taken some marks for that. And this will be the outline of this presentation, which I'll tell you a bit on the significance of structural interpretation in seismic data and hydrocarbon exploration, and then the common fault geometry that we will see on seismic data. It will just be the same with what you learned during structural geology basically, and then how to do structural interpretation on the seismic profiles, and few faults interpretation examples, and we'll do a little bit of structural contouring and isochron or isopach map. So here are some of the significance of the structures. Faults and folds are actually major constituents of the architecture in any sedimentary basin. So as you all know, our hydrocarbon exploration is mainly within the sedimentary basin. So faults, it acts as a formation control for the sedimentary basin and also for the thrust beds in a very large scale of lithosphere. But in a basin scale, the faults directly control the development of structural traps and also the pathway of hydrocarbon and other fluids. This is especially when we have a dipping strata. And in a field scale, when you develop your hydrocarbon fields, faults can act either as conduits or as barriers for the hydrocarbon migration. In the latter case, the main segment of the reservoirs will be dependently divided into few segments or compartments because of these faulting events. This is examples when you have something like very highly faulted area where you have, so this will be the faults, and then you're gonna see your horizons. So it's like that, something like that. So each of these segmented zones contains hydrocarbon. So it's going to be quite difficult for us to drill any of these zones because it is highly segmented with faults, and you know faults can be something very hazardous if you are doing some drilling activities. So if we move to why faults are or structures are very important, because they are the basic constituents of reservoir traps. As example, in a petroleum system, so we have a seal rock and it is bounded by a fault. So this fault actually acts as a bottom seal or a sealing fault. So it prevents the hydrocarbon from migrating to the other sides of the walls, like hanging walls or the foot walls. So if you have your faults here and your dipping strata here which contain the hydrocarbon reservoir, it means that these faults act as a barrier so that the hydrocarbon did not move upwards. And then the faults also act as a migration pathway. So if you imagine that within the source rock you have faults, so how does the oil would like to migrate to the reservoir rock? So it will definitely find a pathway, and faults will serve as a migration pathway for the oil. Faults can either be seal or a conduit as a migration pathway, as I mentioned. So this is examples of faults that we see in our field trip if we go for outcrop. So this is actually examples from Miri formation in Miri. So you have horse and graben structures here. So what does it look like if we have things in seismic data? So basically this is just a schematic drawing showing some of the geometries of that we usually see in the seismic data. So we're going to see planar non-rotational faults, which is our normal faults. We can also see some rotational faults, which is usually created by that created half and graben structure. So few of the students already sees this structure during the lab yesterday. Even we also have Lystric faults. So you know Lystric fault is a very large, big major faults that curves from the top part until a decollement layer at the bottom. So this is you should remember back what you have learned with structural geology. And a planar faults is examples here. It's like a dominoes faults. It's a single or branching isolated structures that do not merge at depth. If a Lystric fault, they will merge at the depth section. So as example, let me show you something like so this gonna be a Lystric fault. So it's merging at the layer, at the bottom layer. So while a planar fault is just ending at certain strata. A planar fault can be varies at angles, usually 60 degrees, 45 degrees, or 30 degrees, and it's form an important group of extensional faults, in particularly extensional setting of reef basins. The large extensional faults can actually cut the entire seismogenic layer. This means the whole subsurface layer up to 15 kilometer. While a Lystric fault is actually, as you all know, is a curved fault that concave up profiles. It has a characteristics of gravity-induced deformation, where the gravity-induced deformation is here, where we have this rollover anticline. Because of the gravity, sediments will tend to move downwards towards the fault. So in a seismic section, usually what we are seeing is sedimentation in this part is thinner compared to sedimentation in this part. So this is just a schematic drawing, but some of you already see this in our class yesterday. So Lystric faults are seismic. The fault slip by the downslope movement of the hanging wall, and the angle of the fault, if you can notice here, that in the shallow section, the faults are quite steep. This is about, I would say, 60-70 degrees, but it become very shallowing angle in the deeper part, because it tends to become horizontal when it hits the decollement layer. Another important fault that is quite significant in our seismic interpretation is conjugate faults. This is where hydrocarbon exploration usually tend to look at, but it is very difficult and very challenging, I would say, because conjugate fault demonstrate the close relationship between crossing conjugate faults and also hydrocarbon accumulation, where we have segmented reservoir and compartmentalization reservoir. If you remember, we have, if you see here, we have 1, 2, and 3 faults there. So what we can see here, these faults actually branching up to the depth section, and we have hydrocarbon here, we have hydrocarbon in the middle, we have hydrocarbon in the middle. So they develop few compartments for this hydrocarbon to accumulate, and it is kind of difficult if we would like to drill at this section. So how can we reach this oil? Because our well is here. So this is usually what geophysicist needs to come out and sits together with the drilling engineer. So the unique conjugate assemblage of this crossing X pattern of normal faults will offer abundant traps for hydrocarbon accumulations, and it will involve many faulted blocks, some anticlines, some syncline, because the compression within this zone will create something like that, and it looks like an anticline. Okay, by the way, just for you to imagine, when we go for fieldwork, we will take notes on our notebook. So as a geologist, we filter out what we would like to do. We would like to take notes during the field trip. So we will just collect information at the outcrops. So location between two outcrops, we have roads, we have trees, those things we did not collect. So we filter our information. But for geophysicists, when we acquire the seismic, we record all the data, including the noise, including our lithologic layers, and also other things. So later on, we will filter during the seismic processing, and when it comes to the interpreter, it is the job of the interpreter to comes out with a geological relevant interpretation on the seismic data. So how to pick structural data on seismic profiles? Basically, we can do this interpretation either in 2D or 3D seismic data. So it's 2-dimension or 3-dimension, and it is very time-consuming process. Interpretation can focus either on a large-scale mapping of basin, means we have a very long seismic lines. However, it can also focus on a detailed specific of a basin scale. Usually what we produce from our fault interpretation using the modern software is known as a fault sticks. As you see here, the first result is our fault stick or fault model, and then we do some grading, and then we overlay with our horizon surface, and then we develop our model. So the end product will be our integration between our horizons, models, and our faults model. Usually we do some attribute analysis on the seismic data, such as instantaneous dip, variance, coherence, and so on. So you are not going to learn about attributes that are specifically for structural interpretation in this subject, because that's going to be in your seismic attributes. So I would like to share with you some of the tips how to detect or extract useful information for structural data from the seismic. Okay, basically our seismic reflection data is biased towards the horizontal reflectors, and steeply dipping interfaces cannot be imaged properly. Basically, I would say this is properly not at all. It's just not imaged properly. Okay. So some basics that interpreters looks for in detecting a structural features is actually truncations, discontinuity, amplitude loss, and also king axis and growth strata. So let's look at for the truncations and discontinuities. Look at here in this black and white diagram where we have our faults at this point. So you can see that the patterns is basically changing from a dipping strata, basically like that, in this area, to a strata that showing something like that. So you know there is some termination patterns, and usually we have we know this as an on-lap or down-lap pattern. We can see the changes of the pattern in seismic reflectors, and you can see that they show some discontinuities within this zone, and even the amplitudes are not the same. The reflectors are showing loss of amplitudes. Even here you can see in these examples that we use in the lab, this is the faults. We even have another faults there. So you can see the characteristics of reflectors are different, and we can also see some subtle truncations here, because the changes is something like that, slightly dipping differently. So this is another example. We have a decollement layer. That's what we pick. So this is actually the strata that coming up on top of it. So you can see there's actually changes in the reflectors. So this is a possible structural event. If you have a larger data size, you're gonna see that this fault is actually extracted like that, something like that. Okay. Apart from that, if you have something, so you see the loss of amplitude in this zone, this part, and you see the reflections are actually like this. And then this, and in the A zone, it's actually dipping differently compared to the B zone. So this is actually usually related to fault and fold. So when you have a faulting event in a dipping angle, some of your strata is going to grow, showing some growth history on top of it. As example, a small example of king band image. So we call this as a king band image. This part, it shows a curved nature of the hinge regions, where the axial surface are relatively straightforward to position. So we know where the axial plane, but it is difficult for us to determine until where the axial continues. So let's see. If we have this, we can see B clearly, the section. We can see A clearly, but we can also see for C, this noted here, is poorly detected in seismic data. This is where we learn about our triangularity in our structural geology. So this is the part where we see our growth. Basically, this is just an imaginary line. Your imaginary line, this part. But it is very important. Why? Because it shows where B part and A part connected and disappears. And within C zone, you can see some growth of strata. Okay, the most important thing is this growth. You can see that it is slightly curvy. The section of D layers to the right side is thinner compared to the section of growth in the left side. So it shows that the growth strata is accumulated on and around the structure during the growth. Means at the same time of deposition of D layers, the structures are pushing up the D layers. So when they deposited, they follow the trend of the structures underneath it. So we know this as a growth strata, and we call D as a growth strata. Sorry, that's my camera, so I have putting my hands there actually. So this is just a summary of what I've been explaining. So D is the growth strata, A is the active axial surface, so it's moving. So A is my green pen, while B is my orange pen. So A is moving and it push. A is moving and push the strata in D. C shows where the pushing finish actually, pushing activities, or we know that as a growth axial surface. So when we do our fault interpretation in seismic data using a modern software, which like Petrel, OpenDetect, Kingdom, and so on, we actually need to create fault sticks point by point. So the creation of these fault sticks in the end will be triangulated and grid into a series of fault planes. So these sticks are typically picked on the seismic section perpendicular to the fault. So but as examples, you have lots of sections seismic, so you pick in one sections and then you move to the other sections. So this will be in the line 1, so this will be in line 1, pick in line 2, and then pick in line 3. So at the end, you combine all this fault interpretation into one particular fault plane. Okay, and this is actually what you see on your seismic. Okay, this is example what a more clear example. So you can see that we have 1, 2, 3, 4, and we have 5 faults. So means that this interpreter already interpret in 5 lines, and then they combine the interpretation as a fault plane. And this is the orientation of the seismic line. So when interpreting a fault, it is very critical to appreciate how the geometry of the faults varies with the angle of observation. So if you see this symbol, this kind of symbol, it shows that the line intersect normally on a fault trend, and the apparent fault geometry displays a true angle of the fault. So this is example in the map. So this is map view. while this is in the section view. If you have your line intersect like this, the intersection will be obliquely on fault trend, so you can see your trend is like that. However, if you are having some growth faults or faults that curvy like least strip faults, the line intersection is as across the curve faults, and it will appear as least strip fault geometry merely due to the curvature in the map view. Is the line intersection along a curve fault also one single fault creates two offsets, if you see here. Bottom of the fault here will not show any offset, any displacement. It just shows like a U shape like that, and actually this part is being faulted. However, we have to be careful when we are doing some fault interpretation. This is because of velocity issue. Okay, the reason is seismic is acquired in time, but our true geology is in depth. So what we need to do is sometimes the things that we see like a least strip faults in a seismic section in time domain, but when we convert it into depth section, it's actually just a planar fault, a normal planar fault. There's no changes in the degree of dipping angles. So this is due to velocity. You can read all the descriptions there, but I'm explaining through the diagrams I'm drawing there. Okay, this is some of the examples of fault interpretation. So just imagine without the interpretation on B sections, we can see few faults, right? Some displacement there. Okay, few here, maybe there, a bit there. So this is usually what geologists did. After the interpretation, we come up with a simple 2D model. Okay, come up with these examples. If you have a 3D data, you're going to have a time slice. So this is a top view at this particular time, the red lines. So in these zones, we can see faults there, here, here. So how do I pick the fault? Because I see the offsets in the horizons. So basically this is the horizons, there, like that. Okay, so I should be using different colors actually. So this one, this one, this one, and so on. Okay, you can see the offsets, this is loss of amplitude, pattern changes basically. So I use all the basic knowledge of faults interpretation to pick simple faults here. And in a top view of this line at this particular time, this is what we see in a time slice. So this is examples of time slice in 3D data, and then you have these variance attributes. So I apply some attributes, and you can see some fault. So you can see your faults are tally with what you have in your cross-section and a top view map. If you don't understand this, please let me know later on after you finish your viewing this, listening to this video. Okay, fault interpretation, some case study. Let's have a look on Gulf of Mexico 3D seismic data. So this is examples that we have, and this is in the map view. Map, all right. Another examples, very complex, even you have lots of faults and you have some, if you see in reality, it looks like an anticline. And faults at different stages, size, angles, and we correlated them with our horizons. So some examples from offshore Malaysia showing very segmented zones with a lot of planar faults, and it shows some bright amplitude events that represents oil saturated sandstone. So these are the higher amplitude, where we call as direct hydrocarbon indicator. Another examples, the faults. So we pick the faults, we can see this is your horizons. The most important thing is you pick your horizons, and then you can correlate with your faults. So you can see series of faults actually in this. And this is very small scale faults, but it's very important for hydrocarbon exploration. Another examples, a real example from North Sea. showing an apparently complex fault geometry as a result of undulation in map view. So you see, very highly complex segmented. So all these segments are actually faulted. These are all faults. But we couldn't see much in the cross sections because of the quality of the data actually. So this is another example from North Sea. You see that the faults appears to have variable depth, but this is just a consequence of different angles of incidence in seismic section. Basically, they are the same fault, fault 1 and fault 1, but at different intersections. So this is in line 1, it shows like that, but in line 2, it shows like that. But when you pick few and a few like that, so we will have a fault sticks, a fault plane. So this is fault 1, fault 2, and fault 3, even though it's showing different angles, but when you develop a whole 3D view, it's going to be a nice fault plane. So that is fault contouring inside in modern seismic interpretation software. So apart from that, we also have isochron or isopach map. Isochron mapping is one of the fundamental seismic interpretation deliverables, and it's actually provide a direction of representation of the reservoir movement, source rock thickness, seal distribution, and so on. It provides clues to understand the tectonic activity and can be directly used as paleogeographical or paleostructure indicator. Isopach is actually isochrons is actually calculated from time structure seismic horizons interpreted in 2D or 3D data, and the value of the map will be typically in two-way time. Okay. But for isopach is another term, is actually a true thickness or absolute thickness measured in meters. So this is in depth. So how to create this? We have manuals to follow and so on, but you don't have to worry because this is actually the most important thing is you need to know what are isochron or isopach map. This is examples when you have your horizons interpreted and then you overlay with your isopach map. So how to create an isopach or isochron map? Be it time data or depth data, you have to pick at least two horizons, so 1 and 2 horizons. So you have to calculate the thickness between these two horizons. So we can see that the thickness varies in the left section and in the right section, also in the middle section, and even here is more thinner. So this is due to faulting events. So these techniques is actually can be utilized. Technique of studying isochron and isopach map can be helpful to know the direction of sediments, accumulations, how thick is your sediments within these two zones, and how it migrated. So in summary, for this lecture, basically we have a lot more to understand about structural interpretation, but basically an interpreter needs to equip him or herself with basic geology first. So they need to know the geometry, the characteristic of a fault before they can start doing the seismic interpretation. They also need to understand how does the folds and faults occur before they just simply interpret. Detecting structures in seismic can be detected or can be interpreted through truncations, discontinuity, pattern change in the reflectors like from flat to dipping, and then some amplitude loss, and also king axis and growth strata. So another one here is growth strata. Growth strata, okay. Faulting and folding are very important in hydrocarbon exploration as it serves as the seal for the hydrocarbon not to move up to another layer, and it's also provide a conduits and migration pathway for the hydrocarbon to move from the source rock to reservoir rock. So I hope you will listen to this, and we're gonna have a little quiz when I come back. So that's all from me. Have a nice weekend and thank you.